This question is about equilibrium reactions. Part A. Hydrogen gas is manufactured by the chemical industry using the reaction of methane and steam. This is a reversible reaction shown in equilibrium 20.1 below. Explain in terms of Le Chatelier's principle the conditions of pressure and temperature for a maximum yield of hydrogen from equilibrium 20.1, and explain why the operational conditions used by the chemical industry may be different. Let's begin by working out the conditions of pressure we need for this equilibrium. We work out conditions of pressure based on which side of the equilibrium has more gaseous moles. And in equilibrium 20.1, we've got 2 gaseous moles on the left and 4 gaseous moles on the right. So the first thing we need to do when answering this question is just state this fact, saying that the right-hand side has more gaseous moles. Molecules are also okay to say, but moles is better because it's a molar ratio we're looking at. And then we need to look at the conditions of pressure. And if there's more gaseous moles on the right, we need a low pressure. Then we can look at the next part of the question, where we're asked about why the chemical industry's conditions are different. Well, firstly, with pressure, a low pressure would have a slow rate of reaction, and because we're trying to produce a lot of hydrogen gas on a large scale, we don't really want something that's going to have a slow rate of reaction, so they might have a slightly higher pressure just to increase this rate of reaction with a slightly lower yield. Then we're going to look at the conditions of temperature we need. So temperature is all to do with the delta H value we've been given, and we're given a positive delta H value. Therefore, we can say that the forward reaction is endothermic. And we know that it's the forward reaction because delta H values are always to do with the forwards reaction, and that will be our first statement that we write because it's positive. You could include this, but it's not essential. It is very important to know, though, for future questions and things to do with equilibrium, endo and exothermic reactions. Then we need to talk about the conditions we need as a result of the forward reaction being endothermic, and that those conditions are a high temperature. If we were to then link to the industry, high temperature would use a lot of fuel and resources, so it's not very good for the environment, and because of climate change that's more important and it's more of a pressing issue. So that would be our reason why chemical industries might not have a high temperature, because it's not very efficient or fuel efficient. To get the 4 marks for this question, we need to explain the conditions of pressure and temperature. You get 3 marks for that, and then 1 mark for talking about the chemical industry. Part B. A chemist investigates the equilibrium reaction between sulfur dioxide, oxygen, and sulfur trioxide, shown below. 1. The chemist mixes sulfur dioxide and oxygen with a catalyst. 2. The chemist compresses the gas mixture to a volume of 400 centimeters cubed. 3. The mixture is heated to a constant temperature and is allowed to reach equilibrium without changing the total gas volume. The equilibrium mixture contains 0.0540 moles of sulfur dioxide and 0.0270 moles of oxygen. At the temperature used, the numerical value of Kc is 3.045 times 10 to the 4 decimeters cubed per moles. Part 1. Write the expression for Kc and the units of Kc for this equilibrium. When working out an expression for Kc and the units for Kc, you refer back to the equilibrium and include all reactants or products in the same state. So, our expression for Kc would include all of our reactants and products because they're all gaseous. Our numerator is going to be our product of this equilibrium if we were to go from left to right, we work backwards. So sulfur trioxide raised to the power of 2. It's raised to the power of 2 because of the stoichiometry in the equilibrium reaction. Then we divide by sulfur dioxide raised to the power of 2 multiplied by oxygen raised to the power of 1. If we were then to look at the units for this equilibrium, or for Kc, we would have in our numerator moles per decimeter cubed squared over moles per decimeter cubed cubed. It's moles per decimeter cubed because we've used square brackets to signify concentration. So if we were to rewrite this fraction, we would rewrite it as moles squared decimeters to the minus 6 over moles cubed decimeters to the minus 9. Then, cancelling out, we can cancel out the whole of our moles from our numerator, and then 1 would be left as the moles for the denominator. And then same with the numerator, the decimeters cubed to the minus 6 can be completely cancelled out, and on our denominator we would have minus 3. Rewriting this, we would have 1 over moles per decimeter cubed. Another way of writing that is as moles to the minus 1 decimeters cubed. To get the 2 marks for this question, you need to have the correct expression for Kc using square brackets and the correct raising to the powers, and then the correct units. You can also check the units because in the question we're given the units for Kc of moles to the minus 1 decimeters cubed. Part 2. Determine the amount in moles of sulfur trioxide in the equilibrium mixture at this temperature. Give your answer to an appropriate number of significant figures. Show all of your working. Firstly, let's look at the question. We're told that all gas volumes are compressed to 400 centimeters cubed. That means we're going to take the moles and times it by 1000 divided by 400. 1000 is the number of centimeters cubed in a decimeter cubed, and that equals 2.5. So looking for the moles we're given the moles of sulfur dioxide and the moles of oxygen. So then we can work out their concentrations. The concentration of sulfur dioxide would be 0.054 times by 2.5, which gives us 0.135 moles per decimeter cubed. Same thing with oxygen. We take its moles, 0.027 times by 2.5 equals 0.0675 moles per decimeter cubed. The next thing we need to do is substitute these values into our expression for Kc. We have our value for Kc, and it's 3.045 times 10 to the 4. So, including this in our expression from part 1, we would then write our numerator as sulfur trioxide to the power of 2, the concentration, because we don't know what it is. But we're going to find it out. But then we can also write our concentrations, 0.135 to the power of 2 times by 0.0675. And that's raised to the power of 1, so we don't need to write it. Then we're going to rearrange to find the concentration of sulfur trioxide. That would be square root, quite a large square root, because we're going to take 3.045 times 10 to the 4 and multiply it by the whole denominator. So that would be 0.135 square bracket squared times 0.0675 as our complete denominator multiplied by our value for Kc. That gives us the concentration of sulfur trioxide at 6.12 moles per decimeter cubed. Then we're going to do the reverse to what we did originally, which was take the moles and times by 2.5 to get concentration. This time we're going to take concentration and divide by 2.5 to get the number of moles, and that would be 2.45 moles to 3 significant figures. It's important we write it to 3 significant figures because in the question we're asked to give moles to an appropriate number of significant figures. So on our answer line, we write 2.45. To get the 4 marks for this question, you need to work out the concentration of sulfur dioxide and oxygen. That gets you 1 mark. Then rearranging the expression for Kc to work out the concentration of sulfur trioxide, that gets you 2 marks. And then finally, taking the concentration and dividing by 2.5 gets you your final 4th mark.